Hello everyone. Today I will present our work, Adaptive Cache-based Radial Sampling for Cardiac MRI with Reinforcement Learning. Cardiac sampling shown here has been significant advances with recent reinforcement learning approaches showing promise for optimization. Radial sampling offers unique advances. It provides motion robustness and efficient cache-based center coverage, making it especially suitable for cardiac imaging. Radial sampling creates spoke-like patterns, which is critical in cardiac imaging, where the heart is consistently moving. However, there is a significant gap in the literature. The potential of reinforcement learning for non-Cartesian trajectory optimization, particularly radial sampling, remains largely unexplored. This is exactly what our work aims to address. Our motivation stems from the need for a comprehensive approach to cardiac MRI acceleration. At the center, we have our AI agent that learns to make intelligent sampling decisions. The agent receives information about the current state and must decide on the next action, specifically which radial trajectory to sample next. The process is like this. First, we perform action selection using radial angles and sampling density information. This leads to cache-based sampling where we generate radial trajectory data. The sampled data then goes through MRI reconstruction using IFFT or deep learning. Critically, we incorporate quality assessments that evaluates both global image quality using SSM and PRCR metrics, as well as cardiac-specific metrics. This feeds into our reward calculation, which uses anatomical laws and quality-based rewards to guide the learning process. The agent then performs policy updates using techniques like reverse or gradient-based methods, creating a continuous learning loop that optimizes the sampling strategy over time. This is our network architecture. First, we have a dual branch processing system. The upper branch handles image processing that processes the current reconstructed image. The lower branch manages cache-based processing for frequency domain data. Our cross-rotation fusion mechanism, this allows effective information exchange between the image and cache-based domain through feature projection, color projection, key projection, and value projection operations. The fused information then goes through transformer processing with patch embedding and multi-head teaching mechanisms. Finally, we have adaptive pooling that produces our final policy output, specifically the action probabilities for selecting the next radial sampling angle. This system also generates critical values. This architecture combines dual domain processing with a teaching mechanism, enabling our agent to make informed decisions about radial sampling patterns based on both spatial and frequency domain information. Our multi-component reward architecture combines three essential elements: global quality metrics that assess overall image reconstruction, hard quality metrics that focus specifically on cardiac regions, a hard loss penalty that penalizes poor cardiac region reconstruction. The mathematical formulation is RT, where we balance global and hard-specific structural similarity indices with cardiac region loss gradients. The adaptive weighting strategy. Notice how the weights change during the training phase. Early phase, FRT is greater than beta T. The agent first learns basic reconstruction. Middle phase, FRT is approximately equal to beta T, transitioning between global and local optimization. Later phase, FRT is less than beta T, emphasizing cardiac-specific data. Final phase, beta T is greater than alpha T, fine-tuning for diagnostic accuracy. The bottom graphic shows the progression over 100 training episodes, where the global weight decreases while heart rate increases, creating a natural curriculum learning approach that mirrors clinical diagnostic workflows. On the left, we see the action to angle mapping. Our agent observes the current cat-speed state and learns to select from 180 discrete actions, each corresponding to a specific radial angle. The reward signal guides the agent towards angles that improve reconstruction quality. The action space is discrete, ranging from 0 to 179, representing different angular positions. This provides sufficient granularity while keeping the action space manageable for learning. Our angle generation process uses a Gaussian ratio-based approach. Starting from a base angle, we apply the Gaussian ratio to ensure uniform cat-space coverage. This mathematical relationship, phi n, creates optimal angular distribution. The bottom visualization shows how different trajectories evolve over time. Each trajectory represents a learned sampling pattern, demonstrating how our agent discovers diverse but effective radial configuration. Finally, our cat-speed sampling follows the mathematical formulation M theta and AT. This ensures systematic coverage while allowing for adaptive optimization based on the current reconstruction state. Looking at the visual result, the top row shows the cat-speed sampling patterns, where our method lets to strategically distribute radial lines for optimal coverage. The middle row displays the reconstructed cardiac images, showing clear improvements in image quality and cardiac structure preservation. The bottom row shows the error maps, where red indicates higher reconstruction errors. Notice how our method consistently produces lower errors, especially in cardiac regions. The quantitative results table provides comprehensive metrics. At 12 acceleration, our rigid-based method achieves superior heart rate metrics and the highest Dice score, indicating better structural preservation critical for diagnosis. At 8 acceleration, we maintain this advantage with heart SSM and PCR, while achieving the highest Dice score. At 4 times acceleration, our method achieves excellent performance. Our rigid-based reverse consistently outperforms random sampling and simple SSM-based reverse. The data scores show progressive improvement, indicating better anatomical structural preservation. We maintain competitive global metrics while significantly improving cardiac-specific reconstruction. The method scales efficiently across different acceleration factors, demonstrating robustness. We present a novel reinforcement learning framework for optimizing radial sampling trajectories in accelerated cardiac MRI. Our method demonstrates that intelligent sample pattern selection, guided by anatomically aware reverse, can significantly improve reconstruction quality while maintaining high acceleration factors. The experimental results validate our approach's effectiveness in learning optimal radial sampling strategies that balance global cat-speed coverage with cardiac structural preservation. By incorporating anatomical knowledge into the sampling strategy, our method achieves both efficient cat-speed coverage and reliable cardiac detail preservation. This work opens new possibilities for developing non-cartesian sampling strategies with reinforcement learning, particularly benefiting clinical workflows where both speed and diagnostic accuracy are crucial. Thank you for your attention.